In this video, we're going to verify Gay-Lussac's law, which states that under constant volume, the pressure and temperature of a gas are directly proportional. So what that means is the ratio of the pressure to temperature is going to be constant throughout this experiment. So what we have set up here is have a beaker of water on a hot plate, which is on right now, heating up the water as I talk through this. And while that's heating up, we have here our PASCO 850 interface to collect all our data and display it in our software. Connected to that, we have a PASport dual pressure sensor. This gets connected to our thermal can, which has a small valve on here. Right now it is open. So we will connect the can here to the pressure sensor, and we will leave the valve on for now in the open position. And then we have a quad temperature sensor with a thermistor that is submerged inside our water bath here. It is important that the thermistor is not touching the bottom of the glass or any side of the glass, just to provide accurate measurements of the water itself. So that is heating up here. And so what we're going to do is, before we start collecting any data, we're going to submerge this can in the water, and we'll let it equalize. And while it equalizes, we will then take our data collection from that point. And it'll take a while to get this data up and running because the temperature is going to be increasing very slowly here. So let's get going then. So I'm going to open up Capstone here. And oops. We're going to use a table. Just drag and drop it, and a graph. And make sure we have a third column here. Now would be a good time to close the valve. So it's in the closed position. We're going to select temperature for one column, and then we're going to do pressure for the other. It's important that we set pressure to Kelvin when doing these calculations. Otherwise, you will not see a constant ratio. And then we need to actually make a small calculation here. So we'll open up the calculator, and we'll just call this P over T is equal to, and click on this color triangle and open up our data. And we will select pressure divided by, same thing here, temperature. Make sure to change the unit to Kelvin. We don't need to name our units, but we will anyways. Just call it kilopascal per degree Kelvin. Hit enter. Okay, so we have that in there. We can close the calculator. And then we will select our measurement once again and select the calculation that we just made. So now our table's all set. Next thing to do is set up our graph. We're going to put the temperature on the x-axis. Once again, change that to Kelvin. And then we're going to put the pressure on the y-axis. Now let's select a common sample rate. We'll keep this relatively low because this is going to take place over a long period, so we can actually see these changes in real time. So 2 Hertz. And now make sure that the valve is closed on the can here. We're going to submerge the can in the water carefully. Make sure the thermistor doesn't touch the wall. And we're going to let the can sit in here for a little bit before we actually start data collection, just so the pressure will equalize with the temperature, and then that way both the pressure and temperature will be in sync. We won't have the pressure trying to catch up to the temperature reading while we're collecting. So we'll just wait a little bit longer. I did turn up the heater a little more, so this should hopefully heat the water a little bit faster. All right. Now we just sit and hold this here for a few minutes. As you can see, as we are collecting the data, um, the ratio between the two is staying very much the same. We're having very small increases in temperature. Let me try to increase the hot plate even more. The thermistor is still not touching the glass, which is good. And so you can clearly see just from the table that the ratio of the pressure to temperature is constant. And if we look over at the graph too, that's a very zoomed in view. But if we zoom back out, this will look more like a straight line once we collect a lot more data. But as you can see numerically, the pressure is increasing and the temperature is increasing at the same rate. And thus the ratio between the two is constant. It's also critical that you're holding the can by the stopper, just because being in thermal contact with the metal will skew the results far more. There's some thermal energy transfer from my hand to the stopper to the can, but not very much because the rubber stopper is a very good insulator. All right, well, I think we've collected enough data here to get the point across. So if you continue doing this and maybe start at a higher temperature where the rate of change will be faster, you'll be able to see a much greater range over the length of the data run. So with that, we have confirmed that Gay-Lussac's law is in fact true, and that is confirmed here with our table, at least.